Okay, so let's try and unpack this. Imagine you're running an air quality monitor. You've got it set up right outside a pedestrian zone, maybe near a school or commuter bike path. You're tracking all these invisible compounds in the air, and then all of a sudden you see this spike. It's sharp, it's intense, but then it's gone. A fleeting blip of a chemical called benzene. What is that little blip actually telling us about the air right next to our roads?
That fleeting spike, that blip you're talking about, it really reveals everything. It tells us that pollution isn't some steady, uniform fog.
Hmm.
You can't just rely on a 24-hour average to understand it. No, it's a dynamic, very localized event. It's all dictated by things like driver behavior, cold engines, and surprisingly, these tiny micro weather patterns that can change minute by minute.
Exactly. And that's our mission for this deep dive. We want to connect the very specific science of, well, volatile organic compounds,
Mm.
focusing on benzene, directly to the choices that urban planners are making. We're looking at research that shows how subtle things like the shape of the land or local weather can turn a standard roadside path.
A path built to keep people safe.
Right. A path built for safety into a concentrated chemical plume that traps these harmful compounds right where we breathe.
And that's the central dilemma, isn't it? Are we, in our attempt to ensure physical safety from, car collisions, are we inadvertently putting vulnerable people like kids walking to school directly into the highest pollution zone? So we're going to use student-led observations, chemical definitions, all of it to figure out why this happens and
Yeah.
maybe how we can fix it.
Okay, so let's start with the main player here, benzene. For anyone who isn't a chemist, what exactly is this volatile aromatic gas that just pops up and disappears so quickly?
Well, chemically, benzene is a volatile aromatic hydrocarbon. It is formed naturally, but the concentrations we worry about in cities are, well, they're overwhelmingly from human activity. It's an industrial solvent, sure, but for this discussion, we're really talking about traffic emissions.
And in that urban setting, what are the main sources? What's causing these spikes right by the road?
The biggest source, by far, is vehicle exhaust. We see the highest concentrations when you have cold engines, a lot of stop and go, driving, hard acceleration.
Like in a school drop-off zone.
Exactly like a school drop-off zone or near traffic lights. And while we mostly associate it with gasoline, it is present in diesel emissions too. It's also worth noting that, depending on where you are, other things can contribute. Wood-burning stoves on a cold morning, or even fumes from a nearby workshop.
This idea of volatility, it
Mhm.
seems key to the whole blip mystery. If it evaporates and disperses so fast, how are we even measuring these high peaks before they just vanish?
That's the thing. Because it's so volatile, it gets diluted and broken down really quickly in the wider atmosphere. And that's precisely why sensors hardly ever record a constant high level all day. Instead, what they catch are these really rapid, short-lived pulses, these puffs, that happen when all the conditions line up right next to the source.
Before it has a chance to escape?
Before it can escape, yeah.
Which brings us to this.
Hmm.
This really fascinating observation from the sources. They call it the Monday morning effect. It's just a perfect example of how traffic volume is really part of the story. So what did the measurements show about how the air, the traffic, and the sun all interact on a cold morning?
This is such a great demonstration of micrometeorology. It's all about how these tiny weather systems dictate air quality. So imagine a cold morning. The air is really still and it's layered. It's a phenomenon called thermal stratification or an inversion. The ground is cold, the air right above it is cold and heavy, and it basically acts like an invisible lid.
So all the morning exhaust from the commute, the benzene, the carbon monoxide is just trapped under that lid.
Completely trapped. It just settles and concentrates right there at ground level, at curb level. It's often too low for sensors positioned higher up to even notice it. It's just sitting there, waiting.
And then the sun comes up and acts as the trigger.
Precisely. As the sun rises, it starts to warm up that lowest layer of trapped air. And that warming creates just a little bit of movement, a slight mixing. But that gentle lift is enough. It pushes that concentrated blanket of hidden gases up and into the sensor's range, and that's when you see that sudden dramatic spike.
So the spike on the chart isn't necessarily a new flood of cars. It's the sun lifting up the pollution that was already sitting there for the last hour.
That is the core takeaway. It proves that air quality isn't just about car volume. It hinges on these microclimate conditions minute by minute. You combine that cold, still air with heavy morning traffic, add a little sun, and you've got a peak exposure event.
Okay, that explains why it collects. But now let's go from the roadside right down to the cellular level. When we breathe this stuff in, what is it about benzene's chemical structure that's so problematic for us?
You really have to appreciate its structure. Benzene is defined by its stability. It's a ring of 6 carbon atoms, and the electrons aren't in fixed bonds. They flow freely in this stable cloud over the whole ring. That stability is everything.
So it's tough enough to survive the trip into the body.
Absolutely. That stability, plus the fact that it's highly fat-soluble lipophilic, means it can pass right through our cell membranes. It gets in through the lungs, travels through the blood, and our initial defenses don't really break it down. It's a very effective molecular intruder.
But if the molecule itself is so stable, where does the danger come from? The sources really emphasize that benzene itself isn't the main threat, it's what our body does to it.
That is the critical point. Our body's defense mechanism, mainly the liver, sees this foreign substance and tries to detoxify it. The liver's goal is to make benzene water-soluble so we can get rid of it through urine. The problem is the chemical reactions needed to do that. They create these highly reactive intermediate products.
So these intermediates are like accidental troublemakers created by the body's own cleanup crew.
That's the perfect way to put it. And these reactive intermediates, they are the problem. They're unstable, chemically aggressive, and they can travel to highly active tissues in the body, like our bone marrow.
And why is the bone marrow so vulnerable?
Because bone marrow cells are constantly rapidly dividing to make new blood cells. When these highly reactive molecules encounter DNA during that rapid replication, they can cause damage or mutations. Tissues with high turnover are just much more sensitive.
Which is where the long-term health concerns come from.
That's right. Long-term or high exposure is linked to problems with blood production and, in severe cases, an increased risk for cancers like leukemia. Now, it's really important to put this in context. The small daily spikes from traffic are usually way below the official limit values. But the fact this mechanism exists, where our own detoxification process creates the danger, is why regulators monitor benzene so strictly, especially in industrial settings.
Okay, so this detailed chemistry has to map back to the real world. If benzene is so volatile, why does it get trapped in these pockets right next to the street? This is where that idea of a micro air quality zone comes in.
Exactly. Pollution doesn't just thin out evenly. The sources confirm that these gases get concentrated in specific pockets or plumes where the airflow is blocked or slowed down. That little pocket is the micro air quality zone, and it can be dramatically worse than the air just a few meters away.
So physical things are acting as pollution traps. What kind of traps are we talking about?
Well, the research points to a few things. Low-lying areas, sharp changes in terrain, dense forest edges, even just a simple hedge, they all slow down air movement. And ironically, sometimes our own infrastructure does it too. Things like traffic calming measures or chicanes, they can create these little eddies of air that just hold on to the pollution, the benzene, the ox, all of it, for minutes at a time.
Which directly confirms the curbside reality. The area right next to the road is the absolute worst place to be breathing.
It's the point of highest exposure. The measurements are clear. The air at the curb, exactly where we put sidewalks and bike lanes for kids, is the most burdened. And this isn't theoretical, they measured it. Moving just 5 to 10 meters away drastically cuts the concentration. And if you go, say, 15 meters away into a wooded area, the levels can be almost down to the background average.
That is just a staggering drop for moving less than the length of a bus. It feels like a tiny change in design could have a huge health benefit. What about rain? Does that help clear these gases out?
Only in a very limited way for gases. Rain is great for particulate matter. It washes the bigger particles to the ground. But gaseous pollutants like benzene and NOx, they're just diluted a bit by the moist air. They don't really get washed out. You need wind for that.
Okay, this all leads to the big question. The flawed logic of how we build our roadside infrastructure. We know the science says the curb is a pollution hot zone. So why have we historically kept building bike paths and sidewalks pressed right up against heavy traffic?
It all boils down to a logistical and economic calculation that's dominated planning for decades. The conventional wisdom is simple. It's cheaper, it's faster, and it's legally much easier to just build them right alongside existing roads.
Because you're not buying new land, you don't need new bridges, you're just using the space you already own.
Precisely. The source material even quotes this pragmatic view, saying this solution gives most cyclists safety for the least money. It's an efficiency-first approach that focuses on the immediate, visible risk of a collision.
But the conflict is huge. That logistical logic runs headfirst into the science we've just been talking about. By focusing on physical safety, planners are putting the most vulnerable people right in the chemical danger zone. So the assumption has just been that the risk of a crash outweighs the risk of long-term pollution exposure.
That's the discussion that's finally happening now. For years, traffic engineers focused on preventing physical injury, which is easy to measure. Environmental harm from chemicals is slower, it's less visible in short-term planning. So yes, the old assumption was that physical separation was the only goal, and the air quality trade-off was pretty much ignored because it wasn't an easy thing to measure locally.
So the big takeaway is that safe from cars does not automatically mean cleanest air.
Yeah.
The science is forcing us to see that the convenience of how we place infrastructure might be directly compromising people's health.
Absolutely. The measurements force you to take a more holistic view. You have to balance the collision risk against the environmental load. And given how steeply the pollution levels drop off within just a few meters, the current standard practice looks very hard to defend on health grounds.
So if the science is this clear, what does designing for health actually look like? Especially in places where there is a bit more room to work with.
Well, the observation from the researchers is that we have to use the space we have. We shouldn't automatically default to the expensive asphalt path right at the curb. For cyclists and pedestrians, a stable, firm gravel path that's set back from the road can be perfectly fine, cheaper to maintain, and crucially, a lot cleaner to use.
The buffer zone. It's an inexpensive, elegant solution. Just pull the path back 5, 10, 20 meters.
And that little bit of separation gives you two huge benefits. Much better air quality because you're out of that concentrated plume, and less noise. The pollution just falls off so steeply that a little distance is the most valuable thing you can add.
And there's an irony, too, with things meant to slow down traffic. We put in speed bumps and chicanes for safety, but they force the exact stop-and-go driving, that harsh acceleration that creates those little puffs of benzene.
It's that classic trade-off. You increase friction, meaning stop-and-go driving, and you increase local pollution peaks. A healthier, safer solution in the long run is a smoother, separate path set back from the road. It offers physical safety through distance and cleaner air, all without creating new pollution hotspots.
So the conclusion for planners seems to be that micro-local measurement is just immense. When you actually see how the air behaves, a set-back, nature-friendly path makes so much more sense than an expensive curbside path that puts people in the exhaust zone.
Exactly. The original question from the observers that it just feels wrong to put kids where the pollution is highest is proven to be the most reasonable way to approach this. Health has to be part of the equation, right alongside collision statistics.
This deep dive has really walked us through the whole story, from this stable, volatile molecule to the weird way our own liver makes it dangerous, and finally to the engineering challenge of designing roads that protect our health, not just our bodies. And the science seems so clear. Where we put the path matters just as much as if we put one there at all.
And if you connect this back to the bigger picture, it just shows the profound impact of microtopography on our daily lives. We've seen that a tiny change in wind, a simple hedge, or a small dip in the land can drastically change the pollution you're exposed to over just a few meters.
It really makes you wonder about the hidden costs of convenience.
It does, and that raises an important question for you to think about. If these small, forgotten details in our environment are dictating our chemical exposure in ways we've never really measured, what other parts of our infrastructure are sacrificing clean air for cheap convenience? That realization that a small buffer zone holds such incredible health value is a powerful insight we can all build on.